Hello, SpaceX. My name is Emily Gurniak. I am a recent top graduate from the University of Pennsylvania with a degree in material science and engineering. I'd like to work for SpaceX because I have always been passionate about space travel, and I'm also hardworking, persistent, creative, focused, and resilient. So now, I'd like to talk to you about my engineering experience with research and development. I hope you enjoy. I have diverse materials engineering experience that I believe will be relevant to SpaceX. I'd like to start with my ceramic experience. I worked at Sandia with Dr. John Eilefeld on sodium superionic conductive thin films for battery electrolytes. And my senior design at UPenn was in charge transport in methylammonium lead halide perovskites for photovoltaic and microelectronic applications. So, NASACON. There's a fire hazard in lithium polymer batteries. Solid-state electrolytes are safer because they're more robust against dendrite formations. The state-of-the-art solid-state lithium conductor has a low ion conductivity, so we consider sodium batteries, which have a high ionic conductivity, inexpensive fabrication, high power storage density, and are good for high power applications. So we wanted to synthesize NASACON thin films by solution processing. We want to do impedance spectra to understand ionic conductivity, and we wanted to understand phase structure and microstructure. So the synthesis is essentially mixing together metal organic precursors in a glove box, and you can see all the precursors here in the order in which we add them. For the fabrication, we start with a silicon wafer, we add titanium oxide, we anneal. We add platinum, we anneal. Next there is spin coating of the solution precursor, formation of the gel on the hot plate, then crystallization in the furnace. After crystallization in the furnace, we go back to spin coating to do a total of 3 layers. So X-ray diffraction checks out. We created the phase that we wanted. In some of them, as we'll talk about later, there is a secondary phase. So crystallite size, as we increase silicon content, we have smaller crystallites. And as we increase temperature, we have increased crystallite size, which makes sense considering the relationship between diffusion and temperature. So SEM results, you can actually see the grains, and you'll see in every sample except for x equals 0.25, there are these white splotchy areas. Those are the secondary phase that in the future we would like to be able to not only identify, but eliminate their formation. But that is a future challenge. So you can think of these samples as the platinum electrodes are like a capacitor, and each individual grain is also like a capacitor, but there's also an internal resistance to ion movement. Here's the ionic conductivity results shown in a different way. The highest ionic conductivity is for x equals 0.25, for which there is no secondary phase, and 800 C. So the activation energy is seen here, and it is consistent with what we see in bulk NASACON. So we found that increased silicon content leads to less crystallographic texture and smaller crystallite size. Higher temperature leads to higher crystallite size for any composition. The best ion conductivity is for x equals 0.25 at 800 Celsius. And we can explain the decreases in ionic conductivity with increased silicon by the smaller crystallite sizes. In the future, we want to look at alternative electrodes and substrates that allow higher temperature processing, look at a way to bind the precursors more tightly into a gel, and consider alternative deposition methods. So here are some of the people who helped, and we are actually published in the Journal of the American Ceramic Society, and I am the second author on the paper. Moving on to research at the University of Pennsylvania. So I worked with my senior design partner Debbie Cometa and Dr. Sherry Kagan on charge transport and methylammonium lead halide perovskite materials. So just a brief introduction. Perovskites for solar is a relatively new field, and the efficiency of close to 20% is amazing. It's close to the Shockley-Quasar limit for a single junction. There's a long carrier lifetime, and we wanted to look at some of the many unanswered questions. You can also see on this slide the structure of the perovskite in all of its beauty. So we wanted to optimize the perovskite synthesis. We wanted to do halide substitutions both during synthesis and also after synthesis. We wanted to make solar cells. and we wanted to do some measurements that are not well reported. Only one group had done the non-contact microwave conductivity, and no one had made transistors with these particular perovskites. So the synthesis is essentially mixing powders and solutions under flowing nitrogen in the custom-made 3-necked flask that you can see on this slide. And for fabrication, we did a lot of spin coating, and for making electrodes, we did evaporation by thermal evaporation. So the X-ray diffraction and the SEM check out. The X-ray diffraction results are consistent with the literature, and the SEM shows a good microstructure. So the microwave conductivity results are very exciting. We show the highest microwave conductivity results seen anywhere. And the photoluminescence results show differences in the way that the different samples and different compositions react to photons. And the photoconductivity results show that there is greater conductivity under illumination, which is good for solar cells. The high conductivity is also promising for transistors. So the commonly used hole transport material for these solar cells was not available. We considered alternative hole transport materials. Once we made solar cells that showed diode behavior but not photovoltaic behavior, we realized that the band alignment was not good for photovoltaic behavior. So you would really need to look at the band alignment, ideally before making any solar cells. We tried some doping transistors, but none of them were able to give good charge transport in the channel of the transistor. But we have hope for transistors because of the photoconductivity results. If their photon illumination can give us the charge carriers that we want, it's just a matter of finding the right dopant that can do the same thing. So we accomplished a quality perovskite synthesis, considered other hole transport materials, and got very promising microwave conductivity results. We got very interesting results from the halide post-treatments in terms of environmental degradation, where it simply degraded upon contact with the halide salt in a solution. So in the future, we would want to make solar cells with the spirometad, alter the halide stoichiometry, and look for a solvent that doesn't degrade the perovskite, and look at other transistor doping options. So moving on to when I worked independently in the Kagan lab on bendable transistors. So essentially with nanocrystal electronics, you have these particle-in-a-box artificial atoms that can come together for band-like transport when the wave functions overlap. You can spin coat them onto flexible substrates and produce high-quality transistors. Dr. Yuming Lai did the bending experiment, and they degrade when bent. In neutral axis engineering, you have part of your beam is under compression and under tension, and in theory there is a neutral axis that feels no strain. Our first challenge with this project that we were able to fix was the fact that once you have thick layers of encapsulation, your probe tips cannot reach your source and drain. So I'm just going to go through the fabrication steps so you can see all of the steps that I did. Parylene C is advantageous because it's a room temperature deposition that will not degrade the nanocrystals. And then we would do plasma etching, so reach the contacts, while keeping the active area of the transistor protected. So with the new pattern, we had a decent mobility. We're just doing proof of concept, so we don't need the best mobility, a low threshold voltage, and a good on-off ratio. What I'd like to mention is, as you can see in this photo, that the transistor is bent. This is what I believe caused these transistors to not be air stable. I believe that caused cracks in the encapsulation of aluminum oxide that made them not air stable. So I believe that the way to solve this problem would be to start with a rigid substrate, spin coat my own polymer, or at least have the pre-made captain adhere to this rigid substrate, and then not delaminate until it is at a neutral axis. So there's no bending until we're at a neutral axis. Thank you. Thank you for your time. I hope you found this interesting. I'd love to talk further about the opportunities in materials and process engineering. And now, in the words of the other Buzz, to infinity and beyond.